Okay, picking up where we left off in the last video, we are trying to see if we can come up with the series representation for this new function e to the sine of x simply by manipulating and plugging in the series information from sine of x into the series for e to the x, and see if we can clean that up and come up with the power series representation through terms of degree 3. So what we're going to do is everywhere that e to the x has an x, we're going to write up through degree 3 the series representation for sine. We're just substituting. That's what we're doing. So everywhere that there was an x in e to the x, we're going to write the representation for sine of x. Now we're just going to clean things up, and keeping in mind we only need to go up through degree 3. So those two are fine. I'm going to drop my plus dot 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 right now and just copy this plus down and continue to go with my terms there. Now, what we have there is we have something that has been squared. So we're going to have to multiply those two terms together. And when we're done, that result will be over 2 factorial. That's me copying down that 2 factorial. All right, so let's FOIL things out. That's going to be x squared. If I multiply x times that term, that gives me something that's x to the 4th. I don't need to include that. If I multiply this by that term, that gives me x to the 4th. I don't need to include that. If I multiply this times that, that gives me something that is to a power of 6, x to the 6th. So that first multiplication is the only thing that I need to include. So that was simple. Now we're going to do the same thing here with the next term and see what we need to include. And then after that, we'll pick up our plus dot dot dot. Now recognize we've already done 2 of those. And the only thing that we needed from that quantity squared was x squared. So now I'm just going to multiply that by the term a third time. And so you can clearly see here x cubed is going to be the only thing I'm going to pick up, because that's going to yield me an x to the 5th. So since I'm only concentrating on things up to degree 3, that's all I need to show. So let's clean this up. We'll have 1 plus x minus x cubed over 3 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. And you can see here, if I've done my algebra correctly, that those 2 terms are going to cancel. So up through degree 3 is that right there, because the coefficient of the x cubed term is 0. So here is the power series up through degree 3, the power series for the function e to the sine of x. So very straightforward. Something we definitely could be asked to do, not extremely time consuming on the AP test. Now here it says find the derivative and the integral. We find that for this general term, we do sometimes have the need to take the derivative of it. We rarely have the need to take the integral of it, just by the way that they set up their AP questions for free response. But it is something that we need to practice taking the derivative of, because we do have to do that sometimes. So if we want the derivative with respect to x of this general term, then what that's going to look like with respect to x, the 1 over n factorial is a constant, so that's not going to change. We're still going to have over n factorial. All we're going to do is use the power rule, which says the power pops down front and we reduce the power by 1. On the right-hand side, we simply differentiate term by term. So the derivative of 1 is 0, the derivative of x is 1, the derivative of 1/2 x squared is x. On the next term, the 3 pops down front and cancels the 3 factor in the 3 factorial and just leaves me with 2 factorial. That's an easy way to do that without having to do a lot of algebra. On the next term, the 4 pops down front. That's going to cancel out with the 4 factor in the 4 factorial and leave me 3 factorial. Hopefully you can see what I'm doing there. 4x cubed over 4 times 3 times 2 times 1. Those terms cancel, and what's left is going to be 3 factorial. That's all I'm doing there. So that's what the derivative of the general term and the derivative of the power series would look like. And that's going to yield us a new general term and a new power series. The function is not really involved. We don't know what the function is here. Now, when it comes to integration, we don't really integrate that series general term. They'll ask you to do different things, but I haven't ever seen them ask you to integrate that. So we're just going to concentrate on integrating what's on the right-hand side. And I want to do this because I want you to pay attention to notation. Anytime that you have this definite integral and you want the result to be in terms of x, and we definitely here want the result to be in terms of x, then I want you to know that you're going to have to put things in terms of t. I also want you to recognize that that is just as important as anything else you're doing in this process. Okay, so we could say the integral from 0 up to x of this infinite series, which we're going to write in t, with respect to t, equals that. Now we could find that antiderivative, no problem. That's just the power rule for integrals. But we find that we're really not asked to do that much. So let's term by term find the antiderivative here. We're finding it in terms of t. We're integrating with respect to t. So let's just go about doing that. I want you to realize here this is 1 over 2 factorial times 1/3 t cubed. Well, 2 factorial times 3 is just 3 factorial. Here we're going to get the same thing. We're going to have 1 over, I'll write it one more time, 1 over 3 factorial times 1/4 t to the 4th. 3 factorial times 4 is 4 factorial. So we can go straight on those terms. We can go straight to the new factorial. So it is not as complicated as you might think it is. Now we're going to evaluate this at x. We plug in our upper limit. X to the 4th over 4 factorial, x to the 5th over 5 factorial. Don't forget your plus dot dot dot. There's our upper limit. Now every term has a t in it. And so when I plug in 0 for my lower limit, all I'm going to get is a bunch of zeros. So here is the new power series that is the antiderivative of that general term. All right, let's do one more. We'll do one more example of taking the derivative in the integral. We will take the derivative with respect to x of the general term, just because I want you to see that one more time. And so we want the derivative with respect to x of -1 to the n. That's just a constant. We're differentiating with respect to x. The quantity 2n plus 1 factorial, that's a constant. That's not going to affect anything. So as a matter of fact, I can just write those down because this is the only term that's going to be affected by differentiating with respect to x. It's the only term with an x in it. Everything else is a constant as far as x is concerned. So the power pops down front. We reduce the power by 1. 2n plus 1 minus 1 is just 2n. This is still an infinite series. So we are asked to do that sometimes. If this were a multiple choice, I want you to understand that this would clean up. We have 2n plus 1 over 2n plus 1 times 2n times 2n minus 1, and so forth, right? That's what factorials look like. So those terms cancel. And what we're going to wind up with, this is the quantity 2n factorial. Please make sure you put parentheses around it. This does not equal 2 times n factorial. So be really careful. All right, so now all we have to do is differentiate. So the derivative of x is 1. The derivative here, the 3 pops down front over 3 factorial. This is 3 times 2 times 1. Those two lead terms are going to cancel. So what you're going to wind up with is x squared over 2 factorial. Notice in the next term, the 5 pops down front. It's going to cancel with the 5 in 5 factorial. That's going to be times x to the 4th. And what you're going to have left over is 4 factorial. And you'll see that pattern happen a lot. Here in the next term, the 7 pops down front, cancels with the 7 and the 7 factorial, and leaves us 6 factorial. So this is the series, the power series, for this alternating series. And we were able to find the general term. Lots of times they'll ask you to find the general term. Thankfully, most of the time when they ask that, you're differentiating. All right? So now let's do this same thing, only let's integrate. We would integrate from 0 to x, this infinite power series. The alternating term isn't having any effect. Remember that you are now going to put things in terms of t because of this notation. And that's going to equal the antiderivative of every term on the right-hand side of the equal sign. So the antiderivative of each of those terms, and we would show the AP reader that we recognize this is what we're doing. Please don't forget that you have to show them you recognize you're dealing with a power series. And so that would equal 1/2 t squared. Okay, we would have, again, we're going to have 1 over 3 factorial times 1/4 t to the 4th. So what we're going to get is t to the 4th over 4 factorial, just like in the last problem. Here, we're going to get 1 over 5 factorial times 1/6 t to the 6th. That yields us t to the 6th over 6 factorial. Here, very easily, that's what we're going to get. We're going to evaluate that at x and then at 0. So we have x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial minus x to the 8th over 8 factorial. Now, we recognize when we plug in 0, that's just going to go to 0. You can, if you want to, include that. But understand, since we don't have to simplify, we don't really need to show minus 0. I'm getting my lower limit of integration from the notation on my infinite series, and so that would make a difference if n started at 1 or some other value. So don't just automatically think that's always going to go to 0. It's going to 0 because of where they tell us that n starts.